plan a very long section. So since nobody seems to be like many people are missing, I'll just say what I have to say, and then if you have any questions regarding your projects, we can discuss those. Otherwise, we'll just be done. So today I was going to say a little bit about meta-programming. Actually, let me pull up the page. Here are some resources down here. There are some resources for meta-programming, but I want to explain what meta-programming is. So maybe I think we need an empty screen. Otherwise, people will be looking at the screen. So you will. So meta-programming means that you don't actually write source code that will run afterwards when you compile it, but you write code that somehow controls the programming language itself. So for instance, that would be code that extends the syntax of your programming language. That would be meta-programming. Or maybe macros, if you're familiar with macros. Macros are a technique where some source code that the user wrote gets transformed to some other kind of source code. So that's usually called a macro. Another one would be if you extend your language with a new command that didn't exist before, because that would be meta-programming. That command is then later going to be used by the user to do things. So all these things go under the name of meta-programming. And Lean has a very rich set of facilities that allow the user to do meta-programming. This is not surprising, because in mathematical formalization, you will immediately notice that people want a lot of custom mathematical notation. So that's really important to mathematicians, that they can write their mathematics in a form that is as close as possible to their traditional notation. Of course, you can't do it 100% because some mathematical notation actually does violence to the correctness of what is being written, but you can get pretty close. And so one facility that we would definitely want from a proof assistant is the ability to define new mathematical notation. We're going to look at these examples today, how they're done, how to write that, because I think almost any mathematician who does formalization is going to either have to use mathematical notations defined by others, or will actually want to define mathematical notation for themselves. Now, apart from that, you also have meta-programming facilities such as macros, which are kind of closely connected to syntax anyway. We'll see an example today, but they're more powerful. They are just a way of transforming source code to source code in a more elaborate way that is not necessarily just parsing, because syntax is about figuring out what the strings that were written by the user mean. Whereas macros also allow you to do more elaborate transformations of the syntax. Another one would be defining your own tactics for proving theorems. We're not going to do that today. That's going to be the topic of another lecture. I wanted to keep this lecture sort of shortish and just do syntax today, because I think it's enough. But that would definitely be one that you would want to know. You would want to know about how to write your own tactics. After you get a little bit of familiarity with Lean, you will start seeing opportunities. For instance, you will see that you keep using the same sequence of tactic steps. And so then at the very least, you want to define a little tactic that does that sequence of steps, so you don't have to keep typing it. So that would be the most obvious way of using tactics, but you can also actually write more tactics that do fancy things. And so that we're going to look at that, but not today. So today we're going to just look at syntax a little bit. Now, one thing to understand. Oh, I didn't bring my tablet. One thing to understand is that Whereas the user writes strings, right? When you're the user, you write strings of UTF-8 characters. That is definitely not how you want to process source code in the compiler. In the compiler, the source code, or in the interpreter, or any later stage, any stage except the first one of whatever your programming language is doing, you want to access source code in the form of a tree, because that's what source code is. Source code is really a tree. I wonder if I can actually try to do like a poor man's. I just want to draw one syntax tree, so people understand what I'm talking about. Yeah. It's going to be kind of silly because I don't have the notebook. But if you write something like this, suppose you have like x plus 3 times y plus z, okay? So what does that really mean? There will be different stages of understanding what this means, and this is all going to be by conventions. These are cultural conventions. So the first cultural convention is that you should read this as a string of symbols horizontally from left to right. In some other cultures, it might be right to left, but in our culture, it's left to right. So we want to get away from this cultural thing, which is made for humans, because that's how the human society works, to something more mathematical. Okay, so it's x plus 3 times y plus z. And in fact, in many places, this one would actually look like this, okay, or like this. So let's use this one. So the next thing to know is that this is something that you learn in primary school. Let me also make this a little bit bigger. This is that multiplication has precedence over addition. So with parentheses, we could indicate it like this. Right? This is now more explicit. But we're not done yet, because we also have to explain what's up with this plus. Now, because you know that plus is associative, therefore it doesn't matter which way you put the parentheses. But if you didn't know that plus was associative, then it would matter which way you put the parentheses between the two pluses. And the social convention is that plus associates to the left. And how do you know that? You know that if when you were in primary school, right, when you were told to compute 3 plus 4 plus 5, if you said, well, this is 3 plus 9, and that's 12, some teachers would say, no, you must say this is 7 plus 5, and then it's 12, right? So, we're not in primary school anymore, so we can understand that all of this is just social convention, everything so far, okay? Nevertheless, these kinds of social conventions must be explained to Lean, because people want to use them. So there's some question here about how do you get from the first to the third line. And even after that, there is still this question of what is really this. This is just a sequence of strings, but as a tree, this is going to be some sort of a tree. And now, I'm sorry. Oh, now I can try to draw with my mouse. Let's see how that goes. As a tree, you would write it like this. So the outermost operation is plus, and it has two arguments, which you would write like this, and this argument here is the variable z, and in here we have another plus, and this is x, and here we have the operation times, and this one has a 3 here, and that one has a y. Okay? Now, what I have just done, the passage from the first string all the way to the tree, that's called parsing. And it's actually more complicated than that, but it's a well-understood topic. It was studied in the 60s, in the 70s. People did a lot of, they sort of cleaned stuff up. It's well understood. So we're not going to dwell on this too much, but you have to understand that there is such a phase, and that you should never think in logic. So if you read an old enough book on logic or a paper, it doesn't have to be super old, they're going to say things like a well-formed formula is a sequence of symbols such that all parentheses match, blah, blah, blah. Okay, please don't think like that, okay? It's okay, people in the old days, they thought like that. It's a tree. It's just written as a string of symbols. If you want to discuss how to convert strings of symbols to mathematical objects that we really study, which is the trees, the syntax trees, that's called parsing. That's a separate topic. It's well understood. Computer scientists know it a lot better than logicians, and so they should do it. If you're going to do logic, expressions are trees. So also for lean, if you're going to do complex manipulations of expressions, you should think about what is going on with trees, expression trees. These are called expression trees. And in lean, they would be defined as an inductive type, which they are. And we can look at it, and it's fairly simple. It's not that complicated. You can actually understand what it does. So anyhow, now let's talk about how do we explain to lean that there is such a thing as plus, and that plus is written between its arguments, and that it has a certain associativity and stuff like that, okay? So that's meta-programming. That's what I mean by meta-programming. And I have some examples, and I took these examples from the book Meta-Programming in Lean, which is probably the best source for this kind of thing. But if you try to do a fancy example, you will probably want to use the help of Zulip. In practice, whenever I have done some meta-programming in Lean, I quickly ran out of documentation. So you just go to Zulip, people will answer. Eventually, they'll recognize at Zulip that it will be better to just write more books, but they seem happy answering questions. Okay, anyhow, this is it's in the notes. It's recommended reading material for this week. Maybe you don't have to read the whole thing, but at least get familiar with it. I recommend certain chapters. Anyhow, let's try to do these things in Lean. Okay, so here's a Lean thing, and let's first discuss this business that plus, when you see A plus B plus C, you should interpret it as, so where was this? Which one is text? This one. So when you see A plus B plus C, you should interpret this as A plus B plus C. What we say is that that plus is left associative. Please do not worry now about the mathematical meaning of plus, because when I'm discussing syntax, this is just the symbol. The fact that this is addition is just something that was built into you in the kindergarten, okay? So forget about that part. That's called semantics, okay? This is a different topic. So it's left associative. Do you know any examples of right associative operators? So one that happens in programming is this one, which is arrow. When you have an arrow, as in function space, yes, this is interpreted as A to B to C. So this would be right associative. Okay, do we have a non-associative one in practice? So I think one that is non-associative is this one. So if I write this, okay, then interpreting this either this way or this way is wrong, is not what people mean. So if you really want to chain if and only if like this as an infix operator, then you should probably use parentheses. Okay. So this one, I think it's fair to say that it's not a non-associative infix operator. However, there is a close relative, which is, really? This is what space looks like. What is going on? Okay, I give up. Is if you write this one, then I think in practice, in many places, this would be also understood as the same operation. No, sorry, that's the negation of if and only if. It's XOR, right? So no, forget about it, okay? So if and only if, we just don't have it, okay? Another one that is non-associative is equality. A equals B equals C. Nobody interprets this way, right? Okay, so this one is also non-associative. However, let's also clarify that, what's going on? I'm confused about these spaces. Let's also clarify that people do write this. And when they do write this, what do they actually mean? Well, they actually mean A equals B and B equals C. Yes? This is what they usually mean when they write this kind of thing, and similarly for if and only if. So this is a particularly challenging form of notation for somebody who is careful. If you're careless, then you don't have a problem with this. It's often the case that in order to correctly understand humans, you must not be too precise, because then you just get confused because humans are not precise. You have to just keep guessing what they mean. So anyhow, this would be an example of a non-associative operator. And this kind of operation that is called an infix operation is very common in mathematics, because for some reason we really like binary operations. So there are special provisions for this in Lean, which is you can declare new syntax. So let's declare new syntax, where you just say, I have a new infix operator. And you can do it like this. You say, I have a new infix operator, colon, then you put here a number. This is the precedence number. It tells you how strongly it binds. This is to explain things like multiplication comes first and plus comes later. So multiplication should have a higher number than plus associated with it so that it binds more tightly. So there are some numbers here. I never remember, what these numbers are. Suppose you could look them up, and I just kind of try to randomly guess, like give it something, and then when things go wrong, I change it. But I do not. I mean, if you want to be real about it, you check things in the code. Anyhow, here's what you can write. You can say, I have an infix operator here, like this. This is O plus. And then you say what it converts to. So this one, we say it converts to a function which takes L and R, which are the left and the right hand side, because it's an infix operator. It must be a function that takes two arguments. And then you just explain what it is. And this is just the Boolean operators that define X or. So when you do that, you can now use O plus, and it'll just compute. See? Okay? Now, you will notice that there are spaces around here. It would also work without spaces. So what's the difference? The difference is in how things get printed out. And this is important when you have a different form, which is more common, where this is not just like a function. So, by the way this works is it'll really actually directly convert this to functions. So if I say, hey, don't compute true or false, tell me what it is. True, X, or false. And it says, hey, yes, I can tell you that this thing parsed to that expression. See, it literally parsed to the expression applied to true and false. It did no simplification, nothing. It just literally took the function and applied it to the left and the right argument. And I can see that it's of type bool. And when you say evaluate, it computes this stuff. Okay, so a more common way of doing this is to, usually what will happen is you will actually have a function. You define a function like X or. So here's the same function, but it's now defined as a mathematical function, X or, and then you introduce a notation for it. So I write something like this. So here, this one is now different. I'm just using different symbols so that I can demonstrate my point. One is with spaces, the other one is without spaces, but they both expand to just X or. It's a function of two arguments, so it's okay. So when I check this one, it prints fun x x, and then it says ha. So okay, so let's see. This is kind of, let's say this is the other one. Okay, so maybe this is a better way. So first we have the dot, which is XOR, and when I check, I see it's a function. X goes to X dot X, O dot X. Notice there are no spaces around here when it printed out. That's because there are no spaces around here. Okay. And this one I have with spaces. So when I check this one, it says, it gives me spaces. You will also notice that not only is Lean now using this symbol for inputting user source code, but it's also using it already for printing. So when you define an infix operator, if it is bound, if you say that it expands to a particular function, then when Lean sees that function applied to two arguments, it will use the symbol instead, which is of course what you want in 95% of the cases. And in any case, if you wonder what this is, you can hover on it and it'll tell you it's XOR prime. Yep. Okay. Now, suppose you have two of these and you want to, so sometimes you will have more than one of these, and then these precedences get used. And also here, we said it's infix, by the way. So if we say it's infix, let's also do this. It's infix. So what happens if I do three of them? Now it says, I don't know how to parse this because there are two ways to parse this. So I would have to have parentheses like this, and now it's happy. That's because I didn't tell it any associativity. But if I say what the associativity is, say like this, I think it's best to try this one here. Let's try this one. What's going on? I say it's an infix L. Sum. Why does it think it's a sum? Oh, okay. Oh, very good, very good. I'm very happy that we are actually hitting the true complexities of metaprogramming. So let's see. It's happy. It's not happy. Okay. When I write three of them, it starts complaining about sum. True. Okay, so but what is this sum? Okay, so this sum is something that's defined in MATLAB. It's the sum of two types, which already uses the O plus notation. And so that's why it's now confused, because it's trying to figure out what this O plus will be, but it has two notations defined for O plus. It says earlier, somewhere in the Mathlib library, somebody defined O plus to be a certain thing. And the reason that they don't have these problems in the book is because they don't use MATLAB. But if we disable MATLAB, I suspect, no, it's part of Lean. Yeah, no, we're just stuck. So in such cases, it's best if you try to play nice and not override existing notations. So that would be by far the easiest thing to do. So for instance, if here we say, oh, this is XOR, now I can type XOR, XOR. See, it doesn't have to be a symbol. Okay. Let's see what happened here. Okay, so maybe it's better to do it down here with this one. I'm gonna do it here. X, Y, O dot Z. We're going to experiment with what happens when I have different kinds of associativity. So right now, I have left associativity. So if I hover here, it's going to tell me that this O plus binds the whole thing, which means it's the one that comes later, whereas this O plus only binds the X and the Y. If I change this associativity to the right, then it's the other way around. Now this one binds only Y and Z, and this one binds everything. If I say no associativity, now it says I don't know how to parse this. It's ambiguous, and it does not just do a random thing. Yeah, is that clear? Okay. Now, we can also try something else. Sometimes you want to have fancier notation than just infix. But let me first show you that you can define infix using this fancier stuff. Okay, so you can write you can write something like this. You say, I have notation. Instead of infix, you say, I have general notation. So if you want some sort of general notation, you start with notation. You will also notice here that it says scoped. Scoped means that this notation will only work in the current namespace, and the current namespace is my syntax. So as long as you are in opening this namespace, that notation will work. This is important because there are lots of notations that will clash. People try to reuse them. So you have to have a way of limiting your notation. So scoped means only in this namespace. And then you say, oh, we're going to have a notation and its precedence is 10. So that's pretty high, pretty low. So things like, it should be the case that the XOR that I just defined up here, where is it? This XOR that I defined here should be should have precedence over the one that I'm defining now. And this is like just the left part of XOR. It's just something silly. It's not L. It's not really important what this is. Okay, this is just for parsing purposes. But in order to be able to see a little better what's going on, let me do it this way. Okay. We'll see how this works. Okay, so notation at, this says it's at level 10, and then this is now here, you just write what your notation is going to look like, and you put the literals, which is the constants, the symbols that you want to use, the actual symbols that will feature in the notation. You put them in quotes as strings. You already know what the spaces are for. It's for printing out stuff. And then you just say, oh, I'm going to have an argument here. It's the left argument. I'm going to have a right argument. It's here. And you say what the precedence of the arguments is. Okay. And this is a way that you can control left and right associativity. So this says this entire expression will have precedence 10. Whatever is written here can be written without parentheses so long as its precedence is 10 or more. And this says whatever is written here can be written without parentheses so long as its precedence is 11 or more. So the consequence of this is that LXOR will be which, left or right associative? What do you think? So am I allowed to write here L? So let's consider this, okay? So suppose I write A, L, X, or B, L, X, or C, okay? So am I allowed to parse it this way? Am I allowed to parse this expression? Will I succeed in parsing it this way? The answer is yes, I will. Because if I parse this expression, I will get something that is of precedence 10. See? It says when you parse something of this form, its assigned precedence is 10. And this says, so because this is 10, and this guy says, hey, I'm happy with anything that's 10 or higher in this place. It's okay. So this will work. And by the way, a symbol like this has like precedence infinity. Yeah? It's unbreakable. You never have to put parentheses around it. But if you try, so this one is okay because you will say this is my L, and this is my L, and the precedence of thing is declared to be 10, and L can be 10 or more. It's fine. If I try to do it the other way, then this one will fail. Why will it fail? Well, it'll say L is okay because this is just a symbol. Its precedence is very, very high. And so that's more than 10. But the precedence of this one, here is 10, but it should be at least 11. Okay. However, if you put explicit parentheses around it, that is a way to force your precedence to go to infinity. So whenever you have parentheses, the purpose of the parentheses is to raise the precedence to infinity. So it's always okay to write parentheses. That will always help parsing. That's the idea. Okay. So in fact, this infix L thing here is a kind of shorthand for what we just did down here. Now, when you try to combine these things, I renamed it to XOR. Let's try to see what this is. And we don't want to eval, I think we want to check. Okay, so the important bit is we go and we look at, hello, where is, here it is. When we check this thing, you see, it's not printing out, it's printing out LXOR because I defined it as a function, but because XOR, here, this one, is defined as some expression, it doesn't know how to sort of undo the parsing. It only knows how to undo the parsing when the parsing transforms something to a symbol. And then it sees the symbol and it says, oh, I know how to unparse this thing. So we really should be using one of the other ones, like let's use the XOR here. Which one is the O dot? Let's use the O dot here to see how this works. So if I say O dot, now LXOR has precedence 10, O dot has precedence 60, so expect the 61 to bind stronger, and it does. And this one binds. Yeah? If they were both 10, then what did it do? It still succeeded. Okay.
But it's okay, right? Because the O dot operator is on the left of the XOR.
Yes.
And it has precedence 10, and XOR expects
10. Yes, it's okay. Yeah. So it would only be problematic if I declared like everything to be 10 and then it's going to hit an ambiguity. But now there is no, yes, you're correct, totally correct. It's okay because LXOR says, I'm happy if to the left of me there is something with precedence 10 and this guy is there with precedence 10. But it's better not to sort of live on the edge and have like everything at precedence 10. You want to have reasonable precedences.
Sorry, but if it had precedence 9,
let's see. If it had 9, then, well, it parsed. The question is, how did it parse? Now it parsed the other way. Yeah. Okay. Yep. Now, it doesn't have to be a binary operator. Okay. So let's have an exercise. Let's define a notation for overriding function values. So what is the idea? The idea is that given a function f, say from alpha, oops, I'm in lean, I can do this, alpha to beta, and x in alpha and y in beta, define a new function which is like f, except that it maps x to y. Okay? So you have a function and you want to change it at one place. So let's first define the function. Override, we have alpha and beta, and let's say that this is universe polymorphic just for fun. And then we have my f from alpha to beta, and I get the x and the y. And what I want to say is, and I will land, okay, so let's be explicit, x is in alpha, y is in beta. I will get a function from alpha to beta. How is this function going to work? Well, it'll take an x prime. It'll say if x equals x prime, you will have to debug this for me. Then y else f of x prime. Okay? So this is what I want to write. I got an x prime. If it's equal to x, then I override with y. Otherwise, I use the previous value. But there is a bug. What is the bug? Okay. That's a bug I didn't even see. Thank you. Okay, now it's happy with the declaration, but it's still unhappy with this. What does it say? It says, fail to synthesize instance decidable. Now, if you don't know what decidable is, you go here, and it says decidable P is a data carrying class that's a blah, 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 blah. You explore what this says. Or you control click on it and you go to the definition and try to figure out. And there is more here to read. Well, this is what was showing in the small boxes here, or you can go to the proper documentation. But to explain what's going on is, speaking algorithmically, constructively, and generally sanely, when you have a set, you might be asked whether two elements of that set are equal, and you have to give an answer. You give, like here, I have x and x prime in alpha, and I would like to see whether they're equal. Of course, in classical mathematics, this is a total non-issue. Of course, they're equal or they're not equal. However, if you care about computing things, which in Lean you might, it would be very nice if this function actually computes on simple examples where I have, like, if alpha is the natural numbers and beta is the natural numbers, and I put in some specific code with some specific numbers, and then I say evaluate, I want to be able to actually compute the result. Can I do that? Well, for the natural numbers, I can do that. But what if alpha is something fancy? What if alpha, for instance, is infinite sequences of natural numbers? Well, then the x and the x prime will be infinite sequences of natural numbers in general. Can I compute whether two infinite sequences are equal? Well, that seems algorithmically a little fishy, because how are you going to compute whether two infinite sequences of natural numbers are equal? You might say, oh, I will be very smart. I will investigate the source code for those sequences. Point A, you may not have the source code. Not everything has a source code. But even you have the source code, you should open a book on computability, and it'll tell you that you can't do that because you're going to run into the halting oracle. So it's not algorithmically decidable. And if we want to keep track of what is and isn't algorithmically decidable in Lean, there's a way of doing that. With type classes, that's what the decidable type class is about. It's about saying, hey, the type alpha has instance. So decidable means that this particular logical proposition is of the kind where we can actually compute the answer, which is what we need if we want to calculate that function. So what is missing here is the assumption that alpha is the kind of type whose equality is decidable. And that is readily, it's that. Decidable ek is precisely the instance, that says for all a and b in alpha, it is decidable whether they're equal. It's precisely what we needed. So now with this, we actually have a function. So we can try it. Let's see. Override, eval. So let's override something. So let's say we have the function on natural numbers. We have to tell it a little bit about what this stuff is. So natural numbers, or we could just write successor, I suppose. And successor override, I think it has two R's. No, how about this? Nope, there's no not this. Yep, okay. It says, okay, so now it's saying it has type n arrow n arrow n arrow n, and then it complains that it doesn't know how to display such functions. Okay, this is another type class. There's a type class for those types that whose values can be converted to strings for the purpose of showing them to the user. Not everything can be shown to the user easily, like a general function. You might still be thinking source code. No. What if this function? So not necessarily, because not everything is source code. Okay, so anyway, let's keep going. So suppose we want to say when x is 3, this thing should have value 5. So that's my function. Well, what will I get if I evaluate it at 1? I get 2. If I validated 2, I get 3. If I validated 3, I get 5. If I validated 4, I get 5. Okay? It seems to be working. But, you know, that's silly. Okay? Let's invent a new notation. Notation. Oops. No. Notation. Give me a precedence. Pick a number. 50? Sure. Why not? Okay? Give me a notation. How would you like to write these things?
Which is probably the function angle bracket.
Okay, function. Give me a notation. Give me, okay, so something here. Okay, I'm going to put down, we need to think about this later, okay? You want to start with what? Oh, so now you want the angle bracket, okay? Then?
The input value.
X, okay? And it has to have, okay, and then?
Maps to.
Like this? Okay, the output value, like this? Okay. And then this would be override fxy, okay? Without this. Okay, so probably 666 is not the correct number here. Let's think about this. Would we like to chain these so that you can override several values? We would like to chain them. Because we would like to chain them, what would be an appropriate number here? Something lower than 50. Because if it's 50, that means f could already be this notation, and that will allow me to change them. So 50 seems reasonable. This, you know, you don't have to do it, and you can just do it if it's really necessary. Do you want to put any spaces anywhere? Because right now, there are no spaces. Now let's see if this works. Not successor 3 maps to 5 applied to 4. And we have our little notation. Oh, which is kind of nice. Okay, can we do this? 3 maps to 4, and then 10 maps to 0. Seems to be working. 10. Okay, goes to 0. Okay, what if I do this? What will I get when I evaluate at 3? Yeah, I'll get 10, the last, right? Because it goes from inward, it goes inwards. So already the first override, the 3 goes to 10, overrides. And so whatever comes afterwards doesn't matter. Yep. So you can have your own notations. I'd like to show one other kind of notation, which involves bound variables. Who here knows what a bound variable is? Okay, let's pretend we know what a bound variable is. Now, there are notations which involve bound variables, and for those, this kind of simple thing doesn't work. You have to be slightly more advanced, and I think it's kind of a nice stopping point. If you only care about having nice notations in your development, you will, of course, use notation at infix and so on, but occasionally you will want a simple use of a bound variable. I'll show you how to do a simple use of a bound variable. Okay, so let's say, let's go back here. There's a common kind of notation that people use, which is stuff like this. Right? Which is what I mean, what is this? We have subset notation, so subset notation is like this. Whatever. This is well-known subset notation, which says those elements of n that satisfy this condition. But this is, I mean, this also defines a set or a subset or something. But here we don't have a variable. Here we have something else. So this is really an image, right? This is really an image. So it's the image of a function. The function is x maps to x squared plus 1. of all x's ranging over n. Now, as a programming exercise, let's have a slightly more complicated thing where we say something like this. So let's combine both of these. I'm going to combine, let's have a subset with x ranges over n. It has to satisfy this condition. And for every such x, I will take this value, and that's my subset of the codomain, wherever I'm mapping to. This exists in Python as x squared plus 1 for x in range 0. No, I'm mixing Haskell and Python. Pretend there's infinity. Is there a way to say in Python range from 0 onwards?
Is this something you would be able to do in Python? I mean, this is this.
Yeah, it's not good in Haskell. Okay, let's this particular example we can do in Haskell. No, let's just pretend we have what like this. Let's pretend this is well.
Offsets from 4 to
No, I don't want 4. It's this. This actually exists. Okay, so it could be here. Now it's actually Python. Okay. Well, it's not actually Python. For it to be actually Python, you have to say I want a set, not a list. Okay. So in Python, you can say this. You say, I want these values where x ranges over this stuff here, and it has to satisfy this condition. So mathematicians don't really have this mathematical notation, but let's have it as an exercise. Actually, many mathematicians would use this kind of thing, but they would probably put a comma here. Or even worse, they would put an end here. Okay, now why is this one worse? Why do I really hate this one? You all said you understood bound variables. It's because I'm trying to bind a variable in a sub-formula of a formula. That's just insane, okay? The bounders, wherever they are, should be separate. They should not be sub-expressions in some random expression. Although, of course, Lean has that. So in Lean, when you say if H, then A else B, you're binding H so that it appears in A and B. But it's kind of controlled. But, this can just go wrong if you say that there's an and there. So let's do this notation. Now, what will be the problem here? The problem is that this X is supposed to be bound both here and here. Yes? So how do we do that? Okay, so first, let's see how we do this without any notation, okay? So it's a combination of an image and a subset, so I'm going to call it image subset. We're going to have one type alpha and one type beta. I'm making this type alpha explicit because I intend to make it explicit here. But beta is not explicit. Where this is landing needs to be inferred. So beta is implicit. Then I have a map from f of alpha to beta. And then I have p from alpha to prop. So the idea is that we would write it like this. We would write it as f x in alpha p. And now x is bound in f and in p. Well, the way that there's no nice way to match exactly against my definition, but the idea is this part here is f of x, the other part is p of x, okay? So this needs to be a set in beta. A set is nothing else than a function from beta to prop. So I need to define the predicate that tells me which elements of beta are in this subset. So when is y an element of the subset? If there exists an x in alpha, but Lin will know that I mean alpha, x in alpha, such that p of x holds and y equals f of x. So this combines the subset and the image. So mathematically, I think this is totally straightforward. So let's define odd squares. And here's the ugly version of odd squares. So you say image subset, and then you have to give n, and then you have to give both functions like this. And you can imagine that if you're working with set theory, you're really going to get tired of writing this stuff down. Not like this. It's not going to be pleasant. And it's very likely that in your development, you might actually have constructs where, mathematically speaking, you have some much nicer notation. If you write it like this, I mean, sure, you look more like a hermit in a desert who lives without anything, right? Just aesthetically. But why? So let's define the notation. Okay, so the notation would go something like this. So now we're going deeper into syntax. Imagine that this is our desired notation. So the example above, we want to write like this. If you compare, we want to say, now I can delete this here, empty spaces. Okay, so, but you're still trying. Okay, so I'm trying to write it like this. I would say n cross n for this. And then here I say what n ranges over. And I chose the element hood. It would make absolutely no difference if I put a colon here or something else. I want element here, and then I want the condition here. Okay, so the important bit is that I have to tell Lean these parts here, each one of them, I have to explain what kind of a thing it is. These are called syntactic categories. And there are several syntactic categories, and you can define your own. But in this example, we don't need our own syntactic category. We can reuse the ones we already have. So this thing here will be an arbitrary term or an expression. So that's why I write here term. I could assign precedences, but I'm not doing that right now. Forget the precedences right now. I could assign a precedence here also, but I'm not doing that right now, okay? So the precedences can be there. So term, and then whatever is here can be a complex term. Whatever is here can be a complex term. So these are all terms. The bit that is important is that this one here needs to be a variable, which Lean calls it doesn't call it a variable. A variable is a fairly overloaded term, word that can mean many things. It calls it an identifier, which just means like a symbol. Ident stands for an identifier. So this means that when we parse this, we will not be able to write here stuff like n plus n. We'll have to write, it has to be a variable. Okay? And the whole thing, we have to explain that the end result is a syntactic entity, which is in the syntactic class term. We're trying to define terms, not identifiers or some custom thing or like strange stuff that already exists. It's just terms. Okay. But now, once we have this, now Lean will understand that you can write this, but it doesn't know what it converts to. Like, what is this supposed to be? What expression tree is this supposed to be? It says, okay, you told me how to convert a string to a tree, but I need more, like I need to know what to do with it afterwards. Once I have the tree, we need to explain how it elaborates. The word is elaborates. So up here, this was very easy. We said, well, when you see this syntactic entity, this is how you elaborate it. Just convert it to override fxy. Now it can't be that simple because we have bound variables. So we cannot just say, something needs to happen. And so this is what this macro does. Okay. The book explains much more carefully what the macros do. I will explain the basics. Okay. So the macro rules are there to convert one kind of syntax to another kind of syntax. If we don't have them and we try to check something, like let's try to check this. If I say, hey, Lean, what is this? It knows how to parse it, but it says, I don't know how to elaborate it. You told me that this is syntax, but what do I do with it? If I go one line up, where this syntax is not defined, it's a different kind of error. Now it's a syntax error. Now it doesn't even know how to convert this string into a tree. Here it's a syntax error. It says, I have no idea what this is. Here it says, I have some idea what it is, but I need more. So the more is down here. The more here says, now this back quote parenthesis, this is called This is matching on the syntax. Okay, so when you see something that says back quote and then this, it means that in here we are going to try to take apart some syntax that was already parsed. So we're really describing what to do with the syntax after it has been parsed. So we're saying, hey, suppose you successfully parsed the following bit of syntax: open brace, term, which let's call it T. The $T there is for a reason, so that we know that that's the variable we're assigning, $T here, because we're at the meta level. So suppose $T is a term. Suppose, let me call this one X. I think it'll be a little clearer if I call this one X. Suppose we have a term, let's call it $T. Let's suppose we have ident, let's call it $X. Then we have element, then we have this. See, I'm just actually following this pattern that I described up here. Right? I don't have to. I could also say, and suppose we had a plus here, which say, it's possible to parse this way, but this is silly. Okay, I'm just showing you here. You can have any kind of syntax that you try to match against. However, I'm just trying to match against precisely this syntax to give it meaning. So suppose you have these bits. What do you want to convert them to? So here, the back quote thingy means we're going to match against some syntax. And here, the back quote thingy means we're going to construct some syntax. So we take some syntax apart, and then we put it together. This is proper meta-level programming with macros. Okay, and it says, if you see this kind of syntax, convert it to that kind of syntax. What is that? Oh, convert it to image subset, put in the alpha here, then construct this function. And because we indicated that X is an identifier, this will now correctly work with bound variables, and it'll understand that in T, the bound variable X may appear, because it'll go on and it will now subsequently parse this fun using also some other macro rules somewhere that somebody defined. Maybe they're built in, I don't care, but somewhere there is somebody who knows how to parse this fun and elaborate it, and that part will now not be confused about what's what, because X is an identifier, so this will work the way it's expected to. And then, see, we reuse the X here. Oh, dobro jutro, mi smo skoro končali. Okay, so we like literally construct the stuff up here. You following? Any questions? It's a nice first example. So now you check. When you check now, it says, hey, I know what this is. It's image subset. You see, it got elaborated. It's an image subset of blah, 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 blah. Yep. Okay. It's not reverse displaying it. It's not unparsing it. That's a little too wild to expect to be able to unparse arbitrary elaboration after it's been done. That's too much. So it only knows how to unparse these simple cases of infix operators and stuff like that, which is because they're associated with certain symbols. But this is a little too much, so it doesn't know how to do that. And we can now actually define odd squares like this. Say n cross n and ranges over natural numbers such that this condition is satisfied. And just to check that this works, here's a little lemma. For every odd square, there exists an n such that n is 4 times n plus 1, which is, in other words, if you had taken odd square, then it gives the remainder 1 when divided by 4. And here's the proof. Questions? No? Okay, so maybe just in conclusion, I can say what would be next steps after this. Okay, so you might want to have fancier syntax for the kind of thing that Luna is doing, who just walked in conveniently, because you might have what is known as an internal language of a category, where you write down expressions that have variables and bound variables, but then you convert them not to other expressions with bound variables, but to things like morphisms in a category. That's slightly fancier. Should be doable. I think we can improve what we have now, because what we have now is kind of not very nice. So we should try to improve that. So you could have fancier kinds of internal notation. I asked on Zulip yesterday and didn't really get a satisfactory answer. I think seems like nobody's really thought about it very carefully. You might also want to do tactics and new commands, but that's another lecture. That's not today's lecture. When you want to do those things, but as far as syntax goes, this is a good start, and it's going to cover most of what you encounter as a mathematician. The book has more. Okay, so we're going to finish here, unless there are questions right now.
Yeah, I just
Yes.
asked. So on the second line of the macro rules,
Here are line numbers.
186.
186. Yes, this one.
This is not lean code.
This is lean code. It's lean meta code.
Right. This is not. What am I saying?
Okay, let me try to say what this is, and then maybe I have answered your question.
This is like lean syntax we would write. It replaces
yes
syntax with this syntax,
yes
and then just inputs it into.
Yes, when you see the back quote, that means syntax. So if I say, what is X? It says, I have no idea what it is X. If I say this, then it says, it's a name. Does that help? If I say, what is this? It says, it's a natural number. If I say, what is this? It says, it's some sort of syntax, which is a term, but I'm a little bit confused as to what you're trying to do with it. Monads come in, okay? But nevertheless, this is now considered to be just an expression tree. Yep. Okay.
Just regarding bound variables.
Yes.
At the level of parsing the syntax, just when we declare syntax above,
Yes.
it doesn't yet have any idea that the identifier should appear in only two of the terms and not just.
Oh, how does it treat the fact that this identifier may appear here and there?
Yeah.
Okay. So as far as this part here is concerned, you could just have any identifiers anywhere. So if I say, what is this? Okay.
Yeah.
It says, notice that it says elaboration function has not been implemented. So this means it parsed this thing. It got parsed, but it doesn't know what to do with it. So it successfully parsed the X and the Y and the Z, and it knows that they are identifiers. But if I go up here before I define the syntax, now it just doesn't know anything. But now if I say here, well, I mean, it will always succeed in parsing an identifier, I think. So the point is, this does not say anything about the fact that this identifier is going to bind here and here. It just says an identifier will appear in this spot. It's this bit here that actually does the work of binding, because fun will further get elaborated in a way that will bind the variable. It's the fun that knows how to do it.
So at this point, he knows that X should appear in T and be of type alpha.
When it looks at what it got, okay, so the correct answer I think is this. This macro will elaborate the line 186 to line 187. There will be a further elaboration phase that is going to look at what this fun stuff is doing, and that one will be, its duty will be, among other things, to correctly handle this identifier as a bound variable in T. Yeah.
And an identifier is a term can be an identifier.
Yep. It can be a bound variable. It can be a free variable. It can be a meta variable. It can be a sort. It can be a constant, something, something. It can be an application of one expression to another. It can be a lambda expression, apparently. Yes. And we're done. No, we shouldn't be done. It can be a for all. Okay. It can be a let expression. It can be a natural number literal. It can be a metadata. It can be projection from a record. And now I think we're done. Okay? So now you know what Lean knows. Okay? Let's declare victory for today.